Hello everyone, I hope you're doing fine today. Today we're going to have a look into the November 2020 Physical Science Paper 1, and we're going to focus on question 9, which is about electrodynamics. Straight up, let's go to the question. As we see that this is the electrical machine diagram that is shown in 9.1, and we're just going to have a look at the described elements that form this diagram. The first one is the coil. A coil is a conductor, so it means that current will flow through it, or it conducts charges. And the second thing we see is the battery. Battery and the coil. Also, the most visible thing are the two magnets. On the magnets, we see that we have a north pole and we have a south pole. And then the last thing is, forgot to put in the brushes in there. So we have these two elements, the brushes and the slip ring, but we're going to dive into what each element is going to be doing, or what is the essence of each element in this diagram. But let's have a look at question 9.1.1. The question is asking, is this machine a DC motor or a DC generator? So in simple terms, how do we know if we have a generator, and how do we know if we have a motor? My rule of thumb is that once you know what a generator is, then the opposite must be a motor. So in our everyday lives, we use generators to, especially during the load shedding, some companies or some households depend on generators to sort of provide electricity to the households. So how do you turn on a generator? You already know that you'll have to put in a force in order to get electricity. So what you know is that we use a generator to power our households. So it means that for a motor, we don't want electricity, but we want the opposite of what we do as an input to a generator. So in this diagram, we can already see that there is a battery, and if a battery is connected into a loop or a circuit, so if you look here, there is the loop. There is going to be current there, and then from that current we can sort of depict what is going to happen next. So we already know that we're starting with the battery, and this battery will have current flowing through the wire, and the current that is flowing here will be exposed to a magnetic field and will have the coil turning either clockwise or anti-clockwise. So the right answer to this question is that this is a DC motor. How do you know that it's a DC motor? It doesn't generate electricity. It has electricity or sort of voltage supply as the input to the circuit. So 9.1.1, DC motor. We're going to move to 9.1.2. And the question reads as follows: write down the energy conversion that takes place while this machine is in operation. So like I said, that for a generator, it's always nice to look into your everyday examples so that you can easily answer these questions. For generator, we put in power or muscle or human, we interact with the machine so that we can generate electricity. So we already know that we have motion, or we have kinetic energy that is giving us electrical energy. But in this machine, we have electrical energy that is giving us mechanical energy or kinetic energy or motion through this coil. So we already know that a DC motor will convert electrical to mechanical. And mechanical energy can be either, you can call it motion or kinetic, but what we know is that this machine will be moving, and that is very crucial for this question. All right, we're going to dive into the next question, 9.1.3. In this question, they are asking what is the component in A. So they're asking about this guy here. I've already told you that this is a split ring. Now, how do we distinguish between a split ring or a slip ring? So these concepts are important in that we said this is a DC motor, which means that we have current that is moving through this coil in the same direction. It doesn't change directions. And for our electrodynamics, the most important aspect to generate either DC or alternating current is our split or slip rings. So we see that these rings are not attached together, or at some point this side slips from these brushes and goes to the other side, and this one moves from here and goes to the other side. So we have these as rings that look like that. We have the conductor attached there and the conductor attached there. As this conductor rotates either clockwise or anti-clockwise, we have these split rings dislocating from this brush and going to the other brush, and the other one dislocating from this brush to the other brush. And we see that in between here there is a moment where both of these rings are not connected to the brushes. So if we look at another part of the motion, we have the brushes here and we have the slip rings in this manner. So these are split rings in that there is a moment whereby we interchange from this brush to the other brush, and we keep the electrical current moving in the same direction. So these are called split rings for that manner. Alright, now we're going to look at 9.1.4. They are asking about the direction of the coil. I'm just going to erase a few things here so we can work out the direction of the coil. So, like I told you, this machine converts electrical energy to mechanical energy, but it is important to know what do I want to achieve with this mechanical energy. So if this machine rotates, does it rotate this side or the other side? Why is it important to know that? It's because we probably want to turn something to the right or to the left, and we definitely need to know what we're expecting to get if we have this kind of configuration. So we already know that current, conventional current, moves from the positive plate of the battery to the negative plate. So if we just focus on this part of the conductor, the current is moving in this direction. That's the first thing you need to note. The other thing is that the magnetic field is moving from north, always from north to south. And what I want you to capture from this moment, or just general about electrodynamics, is that when we're dealing with motors, we want to find out where or how will our conductor, or in what direction will our conductor be rotating to. So we want to check what force, or in which direction will the force applied on this conductor be pushing it to move towards. But on the generator, we are putting the force, we have the magnetic field, but we would like to know how will the current be flowing. Why am I saying these things is that for motors, we use the Fleming's left hand rule. that will help us determine the direction of motion, so the force that will be applied to our conductor. For generators, we use the right-hand rule, Fleming's right-hand rule. On the left-hand rule, you basically have your thumb telling us about the force that will be applied to the conductor. We have the direction, so your index finger will be telling you about the direction of the magnetic field, and then your current will be in the direction of this finger. So we already know that from that schematic, or from that diagram, we have the direction of magnetic field and we have the direction of current. So how do we place our left-hand rule to sort of give us the force that will be applied to this conductor? We already see that the magnetic field is going towards this direction, so we already know that we need to have the index finger pointing from north to south. But another thing is that the current is moving towards the board, which means that we can't be pointing in this direction if we're looking at this conductor, at this part of the coil. So we have to flip our hand, maintain the direction of the field, try to follow where the current will be going, then we figure out the force. So we know that the force, so this is the magnetic field, this is the current, the force is in this direction. Let's move over to this part of the coil. Current moves in this direction, this side is going down. We maintain the Fleming's left-hand rule. We know that the magnetic field is going in this direction. The current now is moving towards us, so out of the board. And the force will have to be going up. So we already know that at this part of the conductor, the force is going up. So we have our machine rotating in this manner. And this we call anti-clockwise. So it's going in the opposite of our normal clocks. So if we have a clock, we have 12, 6, 3, and 9. We know that the cursors are moving in this direction, and we call that clockwise. So if we have this moving in the opposite direction of what we see normally on the clock, that is anti-clockwise. So this machine is going anti-clockwise. So 9.1.4, we have anti-clockwise. That's it for question 9.1.4. We'll now dive into question 9.2. I'm going to erase all of this. Thank you. Welcome again. We are now looking at question 9.2.1 of the November 2020 question paper 1 of Physical Sciences. The first question is define the RMS voltage. Define the RMS voltage. So, in simple terms, an RMS voltage is basically the AC voltage component that will dissipate the same energy as the DC voltage that equals to the RMS voltage. What am I saying? If we have a sinusoidal wave, that goes basically a sine wave that goes from the positive to the negative side of our y-axis, and we have a DC voltage that sticks to, let's say, y equals to 3. Over time, it's just constant. This one is moving from 0, it goes to the peak. Let's say the peak is 3 also here. It goes to 0, it goes to -3, then it goes back to 0. What I would like you to appreciate in that, it's easy when we're talking about a DC voltage. So DC, if Y we assume is voltage, This is DC voltage, and this is AC voltage. What do I mean by these confusing terms? As I alluded to the question before this one, 9.1, that when we speak of alternating current, we say that the current is changing directions. It goes from the positive side to the negative side. But a DC voltage never changes its sign. It maintains the sign. So in these two waveforms that I've given you here, they give you an example, or rather a picture of what we mean when we talk of a DC voltage. It doesn't have to be a constant line, but it mustn't go below the 0 mark. So AC will definitely go below the 0 mark. And what do we mean when we speak of an RMS? It's easy for DC voltage to, for us to define an average voltage of a DC value, in that we always have this value, and over time it maintains the same shape. But now for an AC or an alternating current, we have the values literally moving from 0 to positive 3 and negative 3. So over time we have this positive sign cancelling out with the negative sign. So the average of this voltage waveform over one period, so if we move from here to the total period, will be 0. And why is this important to note? It's important in that we are saying that the average of this signal is 0, but what information does that tell us about the signal? Nothing. Or rather, it is going to lie ambiguous in that we think there's no signal, whereas there's something. So in electrical systems, we then venture into the RMS voltage. RMS voltage, and literally, as it says, we square this value, we square our signal. So if you square this signal, there won't be any negative values, as we know that a square of 2 is equal to 4, and a square of negative 2 is still equals to 4. So we square our signal, so all the negative side, they go to the positive side. So we square them, and then the value of the peak changes a little bit. You can figure out how it varies. And then we find the mean or an average of that signal when it's squared. And after we find the average, we then find the square root of that. So in simple terms, one will say we have the signal y of t, we square it, we find an average of this over time, and we find the square root, but we sum this. So, and we do this for one period. So over a period of time, so basically that is a small letter t, and we work out this sum to sort of get to the root mean square. So people who are mostly interested in the root mean square can go to the venture of getting in deep into what exactly are we doing when we're performing this integral. But what I want to show you in that, when we speak of RMS, why is it important for AC voltage? It is important in that it gives us an average, or rather a value that will define almost everything about our signal except the frequency, of course. So when you work out that integral I've just erased, you will see that we have the RMS voltage sitting around this point. VRMS, and we have VRMS linking to the peak in this formula. If you just scroll down to the last pages of your question paper, you will find that VRMS is equal to the peak divided by square root 2. So the VRMS is constant throughout time. That's what we are seeing. And Where do we realize that from, or where do we recognize that from? We see that that constant line sort of mimics this value or this voltage waveform that we see here. So when you speak of RMS, we say that it is the AC voltage component. There it is, the AC voltage component that gives us information of how much or what DC voltage value can dissipate the same power as that RMS. And so in simple terms, an RMS we're now moving to question 9.2.2. 9.2.2, it says that we must calculate the resistance of the device. We are given that the device is marked as 200 watts and 220 volts. What is this, or what does this tell us about the device? This value that we see here is the RMS value, and I'm going to repeat again. When we define an AC signal, it is hard to define it by values at specific times. We give information of how it will look like, or the peak of the signal, through the RMS, and this relates, the RMS relates to the peak through the formula I've just shown you that from the question before this one. So this is the RMS. So this is when they designed the device, they said it's going to operate for a maximum, or rather they would like it to perform at the utmost or prescribed conditions that allude to or need 220 VRMS as the input. And then if we operate it at that voltage, we have to be dissipating this much power, or we have to be dissipating an energy that depends on that power. So these are important in that you already know when you are buying a kettle and it's written 20 watts, you definitely know that for a certain voltage it has to dissipate that 20 watts, and from there you can calculate how much energy your device is going to consume. And what will that tell you? Everyone is buying electricity, so they will sort of have a picture that if I turn on my kettle for 2 hours a day, I'm probably going to be dissipating that much energy. So we're going to be using that power that is given in our marking or the device description. So we're going to go to the question 9.2.2, which is asking about the resistance of the device. From the information that I've given you, we have here power and we have RMS. And what relates resistance to these values? We have the formula that power is equal to V squared over R. And let me tell you about the resistance that you are calculating here. You are not using just any value, but the marked values of the device. What does that mean? When they were creating whatever electrical device they were making, they made it such that it has this much resistance that you are going to calculate here. And what will this resistance do? If you change your input voltage, you're not going to get this much power, but what remains constant is the resistance. Of course, there are factors that affect resistance of devices, and for the purpose of this question, and or rather our scope, we're going to say the resistance remains constant, and we can change the input voltages to get a different power. But how do we work out the true resistance of the device? Through this formula, and we use the marked values. So we're going to say we have 200 watts here. 200 equals to 220 squared over R. And we're going to do a cross multiplication of this to have 200 R equals to 220 squared. So our resistance is equal to 220 squared over 200. And this we can calculate it to be, so 220 squared divided by 200, we're going to get 242 ohms. It is important to put in the units as well. We're talking of resistance here, and it's 242 ohms, not amps, not fishes, not tables. It's 242 ohms. Just kidding. So the next question asks us to calculate the energy dissipated by the device in 10 minutes. But before that, they give us the new conditions. Remember what I told you. The device is now connected to 150 volts AC. The device is now connected to 150 volts AC. So we can draw the circuit. There is our voltage source. We have our device here. It is marked as those values, but now it's not being given the 220 volts that we're speaking of, but 150 volts AC. So I'm going to ask you a question and think about it. When they say 150 volts AC, what are they speaking about? Let's just think about that for a second. Hopefully you've figured that out. This is an RMS voltage. It is not the peak of the AC voltage that we're getting here. This is the RMS. So how do we then work out the energy that is dissipated by the device? So as we have seen in the marked ratings of the device, for 220 volts, we have to be dissipating this much power, and we worked out the resistance, which was 242 ohms. But now, for 150 volts, we're not going to be having this much power. We need to work out the new power. From power, we can then calculate how much energy is dissipated for that much time, 10 minutes. So power is equal to V squared over R. The V that we're substituting here is the current voltage input, which is 150 VAC. But the resistance will always remain true for the device. We don't change the nature of the device simply by changing the input voltage. So we have the device, or the power rather, is 150 volts squared over 242. This is going to give us 92.98 watts. 92.98 watts. Now from here we can work out the energy that will be dissipated over a period of 10 minutes. So the energy relates to power through this equation. Energy is equal to power times time. We know that power is in watts, but what are the units for time that will give us energy? We already know that energy is a product of power, of course, over time, but now it is important to not just input minutes here, because we'll have a problem. We'll be calculating energy at different or at rather different units than what is anticipated. So it is very much important to always convert your time to seconds. Of course, we can have watt, minutes, but conventionally, we need to convert this to seconds. So from the time that we're given 10 minutes, 1 minute is formed by how many seconds? 60 seconds. So to now get the x value or the new seconds, we're going to do a cross multiplication here. So our new time is equal to 60 multiplied by 10, which is equal to 600. And from this time, we can then substitute here to say power of 92.98 multiplied by 600 is going to give us 55,785 joules. So that is 55,785.12 joules. The units for energy is joules. That's it for today. Thank you for watching.